Yeah. Okay, so I think it's going on. Okay, so I guess a good afternoon for those that are in Toronto, or good morning actually for those that are in Toronto, good afternoon for those that are in Europe. So I'm going to talk about, this is going to be the first lecture about the course of introduction, well, resolution of singularity, techniques of resolution of singularities in quasianalytic classes. And today I'm going to do an introduction. So the idea is to first do an overview about what is the goals of the course, and a very rough overview, talking about which are the techniques that we're going to see and why they were chosen. And then I'm going to talk about the definition of quasianalytic classes that we're going to use. This is kind of the plan for today. As soon as I talk about which techniques we're going to see, then I'm going to be a little bit more clear about how I plan to organize the course in terms of hours. Let's go. So I would like to start with a rough definition or a rough notion of what resolution of singularity is in its usual context, that is, in the algebraic case. Okay, so let's just consider a polynomial. Let f of x be a polynomial, let's say in R of x. And here we are using the multi-index notation, and I'm going to use this very often. X is equal to x1 x n. So polynomial, I'm going to even write. So roughly, and this is very rough, a resolution of singularities of f is a proper birational map this is called morphism. So if you do not know what birational is, it doesn't, like, there are some notions from algebraic geometry that we're going to use, but we're not going to use many. Particularly, we're not going to even use birational. Of course, it's just to start. It's just good for the category of algebraic in the algebraic case. And proper, we're going to see later on. To Rn, such that M is a smooth variety, and the pullback which we're going to call, we use the notation I'm using here, P star of F, which is in this case is just the composition of F with this morphic pi, is everywhere monomial. That is, so monomial is the goal that we're having here. That is, at every point that we consider in M, there's going to exist a local system of coordinates let's say U equals to U1, UN, such that at those coordinates, we can write F composed with pi over U, where we recall that U is as the local coordinate system that A is going to be by U put on some power alpha here, which really means is the multi-index notation U1, alpha 1, product until UN, alpha n, where this alpha is some power here with the multi-index given by n, which is the dimension of the variety that we started with. The Rn, the dimension of the ambient space that we started with. So very roughly, this is what is going to be a resolution of singularity for us. Kind of the goal here is going to be to replace the polynomials with the quasianalytic classes, as we're going to see. But before looking at this, I just want to talk a little bit about the history of resolution of singularities and to say a couple of words about it. And to do so, let's just look at an example of how this can look. So let's say in R3, so that we make these connections, let's say that we are taking the function f1, f2, f3, given by the quant. Okay. So one thing that you might have noticed is that there is, when we're talking about this revolution of singularities of F, we're really talking about, we're singling out the zero level set of F. This is really the level set we are interested in. So in this case, the zero level set is an algebraic set, which is a cone here. This is X given by F equals to 0. Now, a resolution of singularities of this set is going to be just an application. So actually, the application that we're going to use, which is going to be very simple, is going to be what we call a blowing up, where we're going to replace the point essentially by a projective space. So by a two-dimensional projective space, in this case, which is the space of all of the directions that we have. So of course they have the infinity, but the idea is that if you replace the point by the projective space, then you are separating all of the possible directions, and we're going to get a cone, which is going to be smooth. So we have the variety M, we have our cone here X tilde given by the pullback of this F, and now we have some sort of parametrization of the cone by the cylinder. Now in coordinates, the application that we're doing here, it also has some nice coordinates. So of course, we're not looking at the infinity of the projective space, but just in this chart of the projective space, we have nice looking coordinates of the form P of U1, U2, U3, defined over the entire R3 here, is going to just be given by U1 times U3, U2 times U3, and U3, which implies that F composed with pi of U is given by, if we look at here, U3 to the power 2 times 1, oops, not 1, times U1 square plus U2 square minus 1. And this term here for every point A, it's either going to be a unit, so either we're going to have a point A which does not belong to the zero set of F, to the transform of it, and then this is a unit, we are good. We can make a change of coordinates here to absorb it into the U3 to the 2, or that is one point where F composed with pi of A is equal to 0. Then in this case, we may change the coordinates here. We may note that the gradient of this function is always non-zero over the set X tilde. And therefore, by the implicit function theorem, we can find a way to rewrite it locally just as a monomial like this. So in other words, by the implicit function theorem, there exists a coordinate system U tilde 1, U tilde 2, U tilde 3, such that F composed with pi U tilde is simply going to be given by this U tilde 3 to the square times U tilde 1. Where does U tilde 1 is equal to U1 square or U2 square minus 1. So having a monomization of the function as we talked is very linked to having a parametrization of the set given by F of F equals to 0. Okay, so this is some sort of remark here that I want to make. In the algebraic case, there is a good relation where good is not defined, but it can be, between sets and functions, or better, ideals of functions. And in the history of resolution of singularities in the algebraic case, we normally ask much more about dysmorphism. But the overarching kind of idea here, let's say the overarching idea, or goal, is to find a good parameterization. By good, we have to be precise. The good parameterization of X, the algebraic set. This is kind of a very rough idea of where it's coming from. And this gives us also like a notion about the history, that if we're working with something like this, which is a singular, of course, there's interest for this for a long time. And if we look at this overarching idea, maybe the first result about this kind of operation is the Newton-Poisson theorem, classical Newton-Poisson theorem. And then in a more modern term, as time developed, we have results about resolution of singularities for the case where the set is equal to 2, the dimension of the set is equal to 2, so for surfaces. So here, there's a lot of different notions of resolution of singularities coming from the 19th century here. Later on, for the case of dimension x equals to 3, we have the result of Zariski. And here already, this is 1944, we already have the kind of result, the kind of technique that we're going to talk about converging to some sort of a statement of the result that we're going to use. But I just want to remark that once it comes from the dimension 2, it was not the case. There was not an idea of what is the statement, the best kind of statement we're going to use. This is kind of being developed through time and being put into test through applications. So already here for the Zariski, you appeared in kind of a modern version of what resolution of singularity is going to mean if it's in algebraic geometry. A local resolution is also proved by Zariski before. But it was always expected that a global result, general result for in the algebraic case would be true. And this is the result of Ironak. Sorry. Dimension of X equals to n, the existence Ironak of resolution of singularity is going to be proved in 1964. Of this rough result, but actually a much more precise result about it. Okay? Now, the goal here are techniques of resolution in quasianalytic classes. Which I'm going to call Q. Okay, so this includes, and we're going to see in a moment a little bit better this is going to include, for example, the real or complex analytic, real analytic functions, real analytic class, complex analytic. This also includes algebraic functions, but more interesting and maybe more to the taste of the program includes, for example, classes of same infinity definable functions. In a non-minimal. Polynomially bounded. Structure. In some sense, we are taking some class of function now to describe, in sometimes some sets that we are interested in, and we want to develop a theory, an algebraic theory for it. And since we have a result that has been quite intertwined with the development of algebraic geometry, we would like to see if it can hold for a more general setting. And the kind of setting that we're going to look at are these quasianalytic classes, which includes all of this example here and more. So let me briefly talk now about what are the techniques. Go a little bit down, that have been chosen. So we're going to talk in terms of technique. There's going to be basically three of them. The first one is going to be resolution of singularities. Of ideal sheaves. And if we want to think about this, this is kind of the best possible result that we can translate from the algebraic case to the quasianalytic. Like this is a global result, and it will have an extra hypothesis on it, on the ideal sheaf, which in the algebraic and complex analytic case are really no hypothesis at all. But in the case of quasianalytic or even real analytic, it is actually an hypothesis that have to be considered. Then we're going to see local resolution of singularities. And I'm going to come back about 1 and 2 in a minute. And third, monomialization of morphisms, which we might think of in the same way that we just talked about resolution of a function. It's really looking at the zero locus, the zero set. Now, when we talk about a morphism, we want to look at all of the possible level sets. And this game becomes very interesting when the target has dimension bigger than 1. So it's not just a function going to R, like the polynomial in the beginning, but really something amorphous that goes from a variety of some dimension M to some variety of dimension N, for example, with N bigger than 1. Okay, so the comments here is that, well, 1 and 2, so just some historical comments, first of all. Were proved first by Bierce and Millman. In 1997. So they are already known for 20 years. And I can add also that there is a proof by Valence-Pascal-Wilkie here. Of 2003, which led to important applications, especially in the beginning of the 2000s, right away. 3 is now a new result, so it's mine and of that. Just accepted, so I'm going to put here 2021, which was the year that it was accepted. Right, I'm going to talk about this. As application, so I'm just citing here the results, but we're also going to talk about applications, so let me put them here. We're going to talk about uniformization of sub-quasianalytic set. I'm going to briefly talk about whole line Theorem, theorem, but I'm not a specialist. Which is an important theorem that says that if you take, we're going to talk more about it later on. So I'm just going to say, if you know what it is, you know that it's important. If you don't know what it is, I'm going to be clear later on in the course. And third, partial results and solutions of Q equations. So here, so maybe I can say that this is the theorem from 2003. Here it's going to be works of mine, Wyborski, and Ed in 2017. And fourth, we're going to talk about reclinization. Sub-quasianalytic sets. which go back to a result of Vola and Servi from 2015, and also comes from our paper on modernization. So it's going to be an application on modernization. So a couple of words like 1 and 2 actually imply the first one here, the I. 1 and actually 2 will imply the number 2 here, together with the fiber cutting lemma. Actually, the 2 of the here with the fiber cutting lemma. 3, we're going to actually use the actual resolution of singularities of ideal sheaves. A local result is not going to be enough. And here I want just to make a little statement, right? We're going to look at solutions of equations. So we're going to look at algebraic problems. Kind of the idea here is the uniformization of subquasianalytic sets and the whole space-Wilkes theorem, they are geometrical results. So if you have a geometrical kind of result, then the heuristic is that a local result is probably going to be enough. But if you have an algebraic kind of result, if you have a function theorem kind of result, then you might need to use actually resolutions which are global. And part of the difficulty is that not every time you're going to be able to use these global results. There's going to be a lot of algebraic questions which we do not know how to answer. And we're in a lack of techniques in between the two, and we need to add new arguments. The word here about recognition of subquasianalytic sets, it's going to be an application of modernization of morphisms. And I want to make a remark that this list of techniques is larger. So in their paper, Jean-Philippe and Tamara, they prove what I'm going to call here vertical modernization, which is exactly what you need in order to prove the recognition of subquasianalytic sets. I'm calling them vertical modernization. They call it in their paper modernization. I'm taking the word in modernization of morphisms from algebraic geometry, so I decided to keep it like that. And I'm calling the result vertical modernization. There are other results. You can think of, at least from this heuristic that I just gave, if we're not really interested that the morphism itself is in the class, you can think about triangulations. Of subquasianalytic sets. You can also think about CR parametrizations if you want something about local results or even just pseudo composition. They all can be, to some extent, thought about it as resolution of singularities. So this is in that overarching idea of finding good parameterization for some kind of problem. And this is kind of the theme of resolution of singularities. Now, instead of just in algebraic geometry, where you had one clear result that was the development for centuries, and we tested them in applications, and this was the good result, that the good statement that we had. In quasi-analytic classes, it's not that clear. We have several results that will have different applications for different in different contexts, and then they can be important in different situations. So it's not yet clear what is the convergent result. But I would like to claim that these three, I feel like, and I'm going to try to argue that they are quite important. Well, because the first two are already proved with time, and the third one is new, and I do believe that it's going to have applications, and I want to talk about it. So the plan is that I'm going to talk about the first two for at least 6 hours, from 5 to 6 hours. I'm going to give not a proof of the first, but a proof of the second. And then I'm going to spend 5 hours, maybe in the second one. And there's 1 hour there to play, because I'm sure that I'm going to be late in one of the sections. So this is the plan of the course. Now, just before finishing this introduction and starting to define things that we're going to use later on, that is defining what a quasi-analytic class is precisely, I just want to make a comment about why local result in this category. So why do we need to consider local results? And here, like, I want to fix it's a category, but let's say a class of function, which I'm going to actually define in a bit. But I really want to think of C as either algebraic over a field of characteristics 0, or reanalytic or complex analytic, like the usual ones from algebraic geometry, one of them. And then I said that there is a good relation, right? I said that there is a good relation between sets and function fields. So we say that X is a C set if for every point A in X, there exists a neighborhood of A such that X inter U is just given by some functions there, f1 of, let's say, x, fd of x equals to 0, where fi are functions on this algebraic function defined, or real analytics or complex analytic functions defined over the entire neighborhood. And then we can define the notion of space. Sorry, C space. If, first of all, X is a C set, and OX, which we're going to talk later on, is a function field, is a sheaf of functions. But it cannot be any sheaf of functions. It has to satisfy extra properties in order for it to be actually, like, it cannot just be an algebraic object. It has to be linked to the set itself. So it has to have some sort of coherence between it. And coherent is actually something that is defined in algebraic geometry. So it actually means something. I'm not going to recall the definition of what it is, but it's really saying that with this hypothesis, then this field of functions here really describe the set F. Just as you take all of the functions that are equal to 0 or the quotient of it, it's going to describe our set X in a good way. Okay, so we have sets and spaces. Now we have some sort of, from sets to C set, exists OX such that XOX is a C space, and X is C set, P a proper projection, P of C, oops, P of X is a C set. So in the algebraic case, this is true. And this is not completely true, but you have constructible sets, so I'm going to say that it's also true. We all know that there's going to be the same algebraic, but I'm going to essentially say that this kind here is true. For complex analytic, you do also have a notion. If you have a complex analytic set, then you are going to find some structure, some analytic space is going to be a C space, it's going to be coherent. So this is coming from Ockla's theorem. And you do have this too in terms of the Remmert proper mapping theorem. Now what happens in real analytic is that already this first passage is not going to be true. So here's already not true. You're going to have examples of real analytic sets that admit no structure of real spaces, real analytic spaces. So there's already going to be a difference between working with real analytic sets and working with real analytic spaces. And here projections are also no, you have all the subanalytic sets. Right. So because of this, the first result is going to ask this hypothesis of coherence, actually something weaker, which we're going to talk in the next lecture, because we need it to be a good algebraic structure. Well, the second result is going to be valid for any analytic space and any, quasi-analytic set, not space, set. Any analytic set, real analytic set, or any real analytic space set. Quasi-analytic set. So this is to motivate why we're going to use with local. So in the rest of So in the rest of the lecture today, I just want to talk about the class of functions that we're going to see and give the definitions and everything to set up things for the next course where we're going to see the results about resolution of singularities. Okay. So part 2. Quasi-analytic classes. So I'll start by defining what is a class for us here. So a class C, which is going to be of same infinity function. So I'm not saying it here, but a class will always mean of same infinity. So it's the association to every open set U over n. So I'm going to do it only for the real case of a subalgebra of functions C of U of same infinity functions such that first thing we want it to contain all the restricted polynomials. So C of U, the polynomials restricted to U are contained in C of U. It's going to be called by compositions. Of C mappings. That is maps C. I'll just do it from this stage. U in Rn to some V in Rm, such that all entries of phi are in C. Right, so if you compose it with the projection here, Rm to R, for every one of the projections, then every one of them is going to be in C. And finally, and the one that I'm going to talk the least, I'm going to talk a little bit later on, is that we're going to ask, because we want to do some algebraic geometry with it, that it determines, well, not just because of that, just a very useful thing to have, determines a sheaf of local R algebras of infinity. Rn for all n. So the condition about being a sheaf is something that I'm going to come a little bit back later in an example to see what is the kind of situation that would not be a sheaf. But in general, most of the things that we're going to see are going to satisfy this property kind of immediately. And now that we talked about what is a class, I can talk what is going to be a quasi-analytic class. So these are kind of going to be the minimal definitions that we want to have. We're talking to the subalgebra function, so a class. Then I'm also going to write like this is quasi-analytic if it satisfies 3 axioms. The first one is going to be that is going to be closed by division by a coordinate. That is, if we take a function there, so let's say that we take f, which belongs to, let's see, belongs to Q of U containing Rn, such that f of x is equal to x1 times g of x, g a same infinity function in U, then g is actually in the class of U. In the same way of this kind of setting, so if it is divisible by a monomial, by a coordinate, then the devised function is also in the class. We can also state it in a simple way that C is closed by the inverse function theorem. Recall that if you take a mapping, an infinity mapping with Jacobian, has a determinant which is non-zero, which is not degenerated, then it admits an inverse, which is infinity. And for example, for the analytic case, if the function was analytic, then the inverse is also analytic. So here we're asking the same. If the function, if the morphism is quasi-analytic, we want the inverse to also be in the same class, quasi-analytic in the same class. And third, the quasi-analyticity. So if I'm going to state it with
Andre, you mean Q is closed by an inverse function?
Oh, yes, thanks. Thanks. And the last one is called analyticity. So for all U open and convex and connected, if there exists a and whoops, we don't actually need the quantifier. If I take U open connection and a point in U, then if we take the Taylor at A, which goes from all the quasi-analytic functions over U and goes to the formal power series at A, so that for every A, we associate the Taylor expansion at A, which I'm just going to call with a little hat, the Taylor expansion at A is injective. So in particular, since it contains the polynomials, the function constant equal to 0 belongs there. So immediately we have as a remark that if it's a quasi-analytic class, then it doesn't contain flat functions. It's quasi-analytic, and F is such that 0, then F is constant equal to 0, at least in the same, well, U connected, the remark with U connected. So besides, we can look here and we see that, well, analytic functions, real analytic functions, any complex analytic, if we have done this with Cn instead of Rn, they're both going to be quasi-analytic. So as an immediate examples of this, just as we talked before. So real analytic. Algebraic functions. So algebraic functions over characteristic over a field characteristic 0. They will satisfy all of these properties, like closed by division by a coordinate, certainly. Composition also determines a sheaf, contains the polynomials, they are the algebraics. They are going to satisfy the Taylor expansion, but they do not satisfy the inverse function theorem, at least in the usual Zariski topology. So here we have to change the topology in the Untitled topology. So that we can do this. And more general, so let me see two other examples that we have. and that we're going to talk from time to time, are the Dangerous-Carlin and the quasianalytic Dangerous-Carlin classes. That is the class of same infinity functions class. I think I can. I'm gonna define it, which is defined in the following way. Let M be a sequence of real numbers, of positive real numbers. We're going to say that F belongs to the class Tm of U if F is the same infinity function on U and for all compact set K in U, there exists A and B positive such that any partial derivative of F at a point A is going to be bounded by an exponential here for y in this compact set. So if we just write like this, you're going to recover the usual definition of the usual, one of the characterizations, the analytic characterizations of being analytic. So here the difference is that we add this weight function in alpha here, which are the weights that we're allowed. So it's some sort of control. So it's all of the same infinity function with some sort of controlled derivatives.
Sorry, André?
Yes.
So factorial alpha is the product of the factorials of the alpha I, or is the factorial of the sum of the alpha I?
Yes, sorry. So this is the product. Yeah. Okay. And the remark here is that, so I'm not going to enter in detail, but under extra assumptions, on the sequence n, Cn, which we might write just K, is a quasianalytic class. And then the last example of something that we're going to follow is the class that we talked about, and which I'm not, again, for the examples, I'm going to allow myself to be vague, and I'm going to explain it just after stating the example. So let S be an minimum polynomially bounded structure. Then we take the class Q of F, class of some infinity locally as definable functions. Is quasianalytic. And this follows from a result of Chris Miller from 1995. So the point that I want to make about this class, this four examples, but it's two in particular that we're getting here, quasianalytic classes, and the case of that is coming from polynomial or minimal polynomial bounded structures, is that they are particularly interesting for us because from time to time we can test results via these two in these two examples. But during the course, I'm not going to do that in any explicit way. So I'm just stating this result, and it's common to either work with one or the other class of functions to test possible results. In the case of the Azure Common classes, you have a lot of real complex, not real, but complex analytic tools to work, extra complex analytic tools to work with these classes. We have extension, C1 extension, Dinkin dbar extension. And in the case of a minimum bounded structure, you have other set of techniques coming from logic and model theory and geometrical techniques coming from just working from a minimum polynomial bounded structure that we can use. So we can pose general problems for quasi-analytic classes and later on try to answer it either with one set of examples or the other. It's really good to test out like this. So I wanted to just state them, but I'm actually not going to use them in any precise, like it's not going to be actually necessary to know them in detail through the course. So that's why I'm just giving you a vague idea of where they're coming from and if they're motivating for you. And now the last part, in the last 5 minutes, I just want to say a couple of words about properties. Of quasi-analytic classes. So a couple of properties that are going to be true is that it is closed by the inverse function theorem, and this is going to be equivalent just by following the same proof of calculus closure under the implicit function theorem. Write this in a precise way, just as I wrote in my note. Class is closed under implicit function theorem and by partial differentiation. Maybe to see just one little proof in this last 5 minutes, like how do we prove that it's going to be closed by differentiation? Well, it's kind of simple. We take so consider a function f, which is in Q of U. Let's say that this guy is contained in R n plus 1 with coordinates xy given by x1, xn, y. And the idea is just to show that let's show the partial derivative with respect to y of f also belongs to this class. So the first thing that we're going to remark is that we can define another quasi-analytic function here, which is just consider the function given by g of x, y, z, and it's going to correspond to f of x, y plus z, minus f of xy. So this, just by using it's closed by composition, so this is a quasi-analytic function. Now, since it is and moreover, it's a quasi-analytic function, and moreover, and g of xy 0 is equal to 0. So as a same infinity function, we may write, since it's 0 along all of z equals to 0, we may write that g is equal to z times another function, x, y, z. Since Q is closed by division by a monomial, axiom 1 of Q H actually belongs to the class itself. And now we just have to note that the partial derivation of y of x, y is simply going to be given by h of xy 0, which belongs to Q. So we're going to get that it belongs to Q. And with that, I'm going to finish today presentation. So the next in the next lecture, we're going to talk about a property that does not work in quasi-analytic classes, which is the vice-versa preparation property. And then I'm going to state the global results of resolution singularities and the local results. And the plan is also to cover, since it's a 2 hours lecture, to also cover uniformization of quasi-analytic sets. Okay, so I'll finish right here.